problems on chapter 6. Okay. Last time we were doing this problem. We want to change from expression in rectangular coordinates and polar coordinates. Okay. So what we did first, we said that we can relate x, y to r and theta through the following relations. X equal r cosine theta and y equals to r sine theta. And in order to transform components from UV to VRV theta, we did together the demonstration using this figure here. How can I project U and V on the frame VRV theta? Okay, so it is very simple. If I just do the projection of U and V on VR and of U and V on V theta, I will get the VR component and the V theta component. So what we will do here, we will apply the following formulas for our problem. In our problem, we have U function of x and y. So the first step, I will replace x by r cosine theta and r sine theta. So what do I obtain? If we do the replacement, we have that U is equal to minus k times y. Instead of y, I will put r sine of theta over, if you do x squared plus y squared, it will give you r squared cosine squared theta plus r squared sine theta squared. So it is r squared. And it's predicted because what is r? R represents the magnitude of the position vector of P. Okay? So when you do x squared plus y squared, you will obtain r squared. So this is equal to minus k sine theta over r. This is for U. I will do the same for V. For V, I will replace x and y by their values. So for V, I get V is equal to kx over x squared plus y squared. So it's k times, instead of x, I will put r cosine theta. And over the same, x squared plus y squared, it's r squared. So this is equal to plus k times cosine theta over r. Okay. Now I have UV expressed function of r and theta. The only remaining step is to project U and V in order to get the component along VR, the total component along VR, and the total components along V theta. So now I will use the following transformation to go from UV in rectangular coordinates to VR V theta in polar coordinates. Okay, so it's just a simple replacement. So let us do it. For VR, for example, for VR, it's equal to, what is the value of U? It's minus k sine theta over r. So minus k sine theta over r times cosine theta. So I multiply by cosine theta. Okay, and I have plus v sine theta. So v is k cosine theta r. So it's plus k cosine theta times sine theta over r. As you can see, the two terms will cancel out. Okay, so this is equal to 0. So for this flow, VR is 0. Now to get v theta, I replace, I do the same issue. I replace in the formula. So now for v theta, it's equal to minus u sine theta. So it's minus k sine square of theta over r. Okay, and I have just, if you want, it's plus, because look, u is negative and I multiply by minus u sine theta, so it becomes plus k sine square sine theta square over r. Okay, and then for the second term, I have plus v cosine theta, so it's plus v is k cosine theta over r. So when I multiply by cosine theta, I will obtain cosine square theta, cosine theta square over r. And you know that sine square plus cosine square is 1, which will simplify to k over r. So look, it's much simpler in polar coordinates, the expression, much simpler than the rectangular components coordinates. Okay? Any question on this problem?
ذكر نحن the part اللي وقفنا عليها ديك المره اللي كمان نرجع نسالك عنها هي انه بطريقه الكونفرجن.
Okay,
يعني
you
كيف
want
جبنا
to...
في ار وكيف جبنا في ثيتا؟
Okay, I will re-explain it. So I will re-explain how to relate VR and V theta to U and V. You have that the vector velocity, the velocity vector V, if I work in rectangular components, I can divide it into U along I and V along J. So vector V is UI plus Vj, okay? Now, another method, if I want to express it in polar coordinates. In polar coordinates, we define UR. So by definition, vector UR is the unit vector of the position vector OP. So if at this instant, my particle, let's say, is at this position, okay, then UR is along OP, okay? And U theta is perpendicular to UR. And UR is defined with respect to the horizontal direction by its angle theta, okay? So this is why you can say that for point P, if I work in Cartesian coordinates, I divide it into X and Y, okay? So for OP vector in Cartesian coordinates, it's written as OP equals to Xi plus Yj. While if I want to represent it in polar coordinates, for OP in polar coordinates, it's just along UR, so it's R, UR, okay? Now, for velocity, my purpose now is to change to VR V theta from U and V. So what should I do? All I have to do is to project the components of the vector velocity on VR and V theta. So I know that V vector is divided in rectangular components into U and V. So first I will say, if I want to move to VR V theta, I have that the component of the velocity vector along UR will be equal to what? Will be equal to the projection of U on VR, okay? Plus the projection of U on VR plus the projection of V on VR, okay? So I should do the summation of both, because vector V as a vector is equal to, guys, just 1 second, please. So here, I have that vector V as a vector, so let me put the arrow here, is divided into two components, U along I and V along J, okay? So now if I want to decompose this vector into UR U theta, I can say that this vector will be the summation of component of U along VR plus component of V along VR, okay? And as you can see in this figure, for vector U, for the U component, if you project it on VR, its projection on VR is U cosine theta. So this is the projection of U component, it's U cosine theta. While for V vector, okay, while for the vector V, you know that this angle here is theta. Why? Because V is perpendicular to U and VR is perpendicular to V theta. So the angle between U and VR will be equal to the angle between U and V theta. So this is the angle theta. This is why if you want to project V on VR, you should multiply by sine of theta. Okay, so I can say now that VR in total, the component along R, is equal to the projection of U, which is U cosine of theta, plus the projection of V, which is V sine of theta. Okay, now I will do the same approach for V theta. If I look at my figure, okay, V theta is doing with V an angle of theta. So when I want to project V on V theta, I should do plus V cosine theta. So here, this is U theta, the direction of U theta. If you project V on V theta, you get this vector, this one. The magnitude is V times cosine this angle. So this is why it's V cosine theta here. Now for U, if you look at U, when I projected on V theta is in the negative direction. Why? Because this is, if I do the projection, it will be like this. So this is the projection of U on V theta. It's in downward, it's in the negative direction. And since this angle here is theta, the angle with V theta will be pi over 2 minus theta. So when I project, I do sine. This is why we put minus u sine theta. Okay, and in this way I can transfer from uv coordinates to ur u theta coordinates. Is it clear now?
دكتور
Yes.
يعني الشيء الوحيد اللي لازم نعرفه بهالسؤال انه كيف بنحول من في ار من يو في لفي ار وفي ثيتا. هيدي الرولز انه فينا نقدر نحفظهم. وبعد شغله بس انه satisfying compressibility continuity دائما لازم يكون الفي ار equal لزيرو.
هلا now we will make sure that لا ما خلص اكيد لا يعني حسب الكونديشنز. يعني هون for example هون ثابت VR equals 0. You can have VR هلا بناخذ غير examples. You can have VR different than 0 and satisfy it. What is your condition? You should go to the formula sheet here. To have, if you have polar coordinates, this is your condition for in case you have polar coordinates, this is the general condition. Now, if you have an incompressible flow, it will be reduced to what? If rho is constant, then this term will cancel out, and rho can be taken outside of the integration. Okay? So if you have an incompressible flow, your relation becomes 1 over r del v by the del r dr over del r plus 1 over r del v theta over del theta plus del vz over del z. Now, in case you have more simplification, so for example, if it's 2D, so vz is 0, for example. Okay? And if
نعم هون كان في فيزات صح؟
I cannot hear you.
هون ما كان في فيزات.
هون in this problem no ما كان في فيزات in this problem. It was a 2D problem. في VR و V theta بس نحن بالcalculation ثبتنا انه VR is 0. But it's not always the case. Okay, in this problem it is the case. هلا you can make sure now, you can verify that the flow you obtain verifies the equation. How you will do it? If you replace in your relation, okay, you get that VR is 0. So let us try to make sure that the result we obtain will satisfy the equation. We have VR equals 0 and V theta equals to K over R. This is the result we obtain. Okay, if we replace in this equation, what is the condition? Our condition is that in general, you should have 1 over R del RVR by del R, okay, plus 1 over R del V del of V theta by del theta equals to 0. This is the condition because it's a 2D flow, so no Vz. Now replace in this problem VR is 0, so this term will cancel out because VR is 0. And you got that V theta is K over R. This means what? This means that V theta is only function of R. So when you derive with respect to theta, what do you get? You get 0. Okay, so this derivative del V theta by del theta will be 0 because V theta is only function of R. And then you can verify that this flow satisfies the incompressible equation, incompressible continuity equation in polar coordinates. Okay.
Doctor, we can always use these VR and V theta directly.
We can always use what? VR and V theta. If you don't have motion in Z, yes. If they give you in the given VZ, then you should add also the VZ component. We will do another problems. And each problem will have its own simplifications. Okay?
هو قصد الايكويشنز لما طلعنا في ار وفي ثيتا انه دايما فينا نستعملهم.
Okay, yes, sure. Yes. Okay. Let us continue. Okay, so I will go back to, so a new problem. This is very simple. Try to apply it. Okay, this is also on polar coordinates. Try to do it as a homework if you want. And If you face any problem, tell me. So it's just because it's the same idea before. This is why I will skip it now, because to do a more important problem. So problem 6. Consider a steady 2D incompressible flow of a Newtonian fluid with the velocity field given by u equals to minus 2xy, v equals to y squared minus x squared, and w equals to 0. Does this flow satisfy the conservation of mass? This is the first question. And the second question is to find the pressure field if the pressure at point x equals 0, y equals 0 is equal to PA. So what I want to tell you always, in general, when they ask for a force or pressure, then you should think about linear momentum, okay? So the Navier-Stokes equation. Since here it's a Newtonian fluid, we can apply the Navier-Stokes equation. Now, first, for the continuity equation, what is the condition? Do you hear me?